Right, good morning everybody. I wanted to look at a few questions this morning on firstly dispersion and secondly waves. The first question, I'd like to find a way of making that a bit bigger, but it's full screen already and it's not zoomable, so I'm not quite sure how to do that. So let me just, this is 2007 question 5. And what you may just about be able to see is a sketch on labelled axes 1, 2, 3, 4, -1, -2, -3, -4 of a wave packet in the solid, and they've drawn a dotted curve through the peaks to show the envelope. And the text says the figure shows the profile as a function of x of a wave pulse with its accompanying envelope travelling in the positive direction at time t equals 0. The phase velocity is 1.5 and the group velocity is 1 metre per second. Sketch the profile as a function of x at time t equals 1 second. So, and they're offering, and this is question 5, so they're offering you 7 marks for that. So this is essentially a question about knowing what the phase and the group velocity refer to. So if we need so that's the x-axis, and if you look, you need to now you really do. I do suggest you study this question. I think it's very instructive. In fact, you could say this question was at the back of my mind with everything I was doing with regard to dispersion. I mean, essentially, I've taught you to answer that precise question and almost nothing else. And the second one that I will tell you about, dispersion, is completely off the wall by comparison. This is absolutely straight down the line. If you look at the axis crossings, there's an axis crossing at plus or minus a half. There's an axis crossing at plus or minus 1.5. So the wave's basically got a wavelength of 1, and the envelope peaks at 1, and so you do need a relatively careful sketch. So we need, and it falls down to 0 at about kind of 2.5. So 2.5 becomes 1.5 if the group velocity is 1, and 2.5 becomes 3.5. So there's the new envelope. However, the phase velocity is 1.5 meters per second, so all of those nodes move forward 1.5. So instead of being on half integers, they're on integers, and the central peak, which was here, is now here. So there's an axis crossing here and an axis crossing there, and an axis crossing there. So it must look something like, well, strictly speaking, we need the lower envelope, don't we? Down here somewhere. So that's got to go there. That's got to go all the way down to there, and that's got to go down to there. So instead of having a big peak at the centre of the envelope, we now have a very steep slope between two slightly less than maximal peaks. So in a sense, the peak of the wave amplitude coincides with the axis crossing, but that's the point where the slope is steepest. So that's and that's gained us 5 marks. So that's a very straightforward question, and you simply have to know what the definition of the phase and the group velocity r. Now, let's, by comparison, look at a different dispersion question on 2018. Now, where's 2018 got to? What's that one? Ah, here it is. Now, I tossed up whether to refer to this question at all. I probably ought to be slightly careful what I say, so I won't refer to the fact that I think it's outside the syllabus and completely insane. But let me just tell you what it says. It gives you a crazy differential equation with i's in it for the field phi. So we have d3 phi by dt cubed, and then plus I omega n d2 phi by dt squared, and then minus c squared d3 phi dx squared dt, and minus I omega d d2 phi by, sorry, minus c squared I d2 phi dx squared equals naught. And so far so good, they've given you the equation. C omega n and omega d are positive constants. Show that this equation has wave solutions of the form phi proportional to e to the I. Now, which way around did they do it? Kx minus omega t. So, well, that's relatively straightforward. That's just substitute. And why did they say proportional? They said proportional because this is a linear equation with one phi in every term, and therefore one of the constants is simply a constant, is simply a multiplicative constant on solution. So if I differentiate, every time I differentiate with respect to the time, I bring out a factor of minus I omega, and every time I differentiate with respect to x, I bring out a factor of ikx. So d3 phi dt cubed will be minus I omega cubed times phi, and there'll be a phi in every term, so I'm not going to write that, plus I omega n d2 phi dt squared will be minus I omega squared, minus c squared d2 phi dx squared will be ik squared, and the extra dt minus I omega, and then minus I c squared omega d ik squared. So we just take a deep breath and multiply out all the i's. So minus cubed is minus, I cubed is minus I, so that I think is I omega cubed. Minus I squared is minus, so that's minus I omega n omega squared, and that's still equals naught. I squared is minus, minus, minus is plus, c squared k squared. Oh, but there's an extra minus there, so that's minus I omega, and then I squared is minus plus I c squared k squared omega d equals naught. So if I collect the k squareds on the right and the omega squareds on the left, I can, I think, cancel through an I. and I'm left with omega squared omega minus omega n. That's that term and that term. And this term's gone on over to the other side, equals c squared k squared omega minus omega d, which tidies up relatively nicely to c squared k squared equals omega squared omega minus omega n divided by omega minus omega d. And so far so good, but that we've only actually got 3 marks for doing that, and the next 3 marks are when the first tranche of people fall over, because they're asking you something which hasn't been part of this course at all, which is the values of omega for which the waves cannot propagate. Why might the waves not be able to propagate? Well, here, if we look at this equation, we have c squared k squared, which ought to be positive, equal to something whose sign might change. And so if this, for certain values of omega, this right-hand side here will be negative. And that doesn't prevent this form of solution working. That form of solution will still work. What it prevents is k squared being positive. In fact, if k squared is negative, then k is imaginary. If k is imaginary, then it's either a decaying exponential or a growing exponential. It's not a wave-like solution. And what actually happens, and this is exactly what happens in an absorbing medium, that you get the k vector with an imaginary component, which means that the amplitude diminishes as you propagate through the medium. In this particular case, it doesn't have a real component, so it only has an imaginary component, and the wave can't propagate in that region at all. And this is exactly what happens in the Earth's atmosphere because of the electrons. Now, if they'd asked this on a second-year paper, it would have been entirely legit, because you do all this stuff in the second year. You study systems where the you find the refractive index for a gas containing for a medium containing free electrons, and it has this kind. I mean, it's not exactly this particular example, but it has regions for which k squared is negative, and meaning that the wave can't propagate, and that's why some sorts of radio waves reflect off the electron layer back down to Earth, and other frequencies don't. So in 12 months' time, you'll be extremely familiar with all of this, but expecting you to figure that out now is probably a bit over the top. So let's just try to sketch the right-hand side of that as a function of omega, and they've told us which is bigger. Omega, so we have omega d here and omega n here. The first thing that happens is that this becomes 0 while this is still positive, and so this is an asymptote. So it goes up to there, and then at omega n we have a 0, and at very large omega, this becomes essentially 1, and it just goes as omega squared. So that is c squared k squared, and so the region in which it can't propagate is here between omega n and omega d. Now, the next 8 marks are really quite a lot of work, because there are 4 limits and 2 velocities, and I'm not going to go through the whole set of those, because they really are quite challenging, some of them, and they also, I mean, it's also a slightly hybrid question, because it's drawing in stuff on limits. I can't remember whether limits are on this paper or not. So let's have a look at the phase velocity. So if I divide both sides by omega squared, I get c squared k squared over omega squared, which is c squared divided by the phase velocity squared, and that's equal to omega minus omega n over omega minus omega d. And so v phase squared over c squared is omega minus omega d over omega minus omega n. Now, it's obviously closely related to the last sketch, but actually we'll sketch this one again because this doesn't have the omega squared and it makes a difference, and also it's reciprocated. So there's omega d and there's omega n. So when omega is 0, it takes a finite value. It's omega d over omega n. When the next thing that happens is that omega becomes omega d, which means that it becomes 0, so it goes down here. And then there's a bit that we don't have to worry about because the waves can't propagate, but at omega n, it then goes down to minus infinity, and so, but out here, in the limit of very large omega, it's 1, so there's another branch of the curve here. And just doing that sketch has answered that question for the phase velocity. The phase velocity, so this is v phase, what I've just sketched is v phase squared. So the phase velocity is root omega d over omega n here, it's 0 here, it's 0 here, and it's 1 here, all of those in units of c. So the phase velocity is relatively easy. The group velocity is quite a lot harder, but, and I'm not going to go through all the details of that, but let's just, if we just write omega equals v phase times k, then d omega by dk is v phase plus k. No, that's not much help, is it? That's not much help. We need to do the other thing, because we don't want to differentiate omega with respect to k, we want to differentiate with respect to omega. So if we write k equals omega over v phase, then dk by d omega is 1 over v group is 1 over v phase plus omega d by d omega of 1 over v phase. So actually it would be helpful to have a sketch of the reciprocal of that. So this is a sketch of, that was a sketch of v phase squared over c squared. This is going to be a sketch of c squared over v phase squared, which will do that, and then it will do that. So that's an asymptote there. So that just tells us what we need to know. So in the limit of, so 1 over v phase is the square root of this, which makes some difference, no doubt. But so 1 over v group is 1 over v phase plus omega times the derivative of 1 over v phase. So the derivatives here and here, you'll notice, are infinite. So the group velocities actually go to infinity at the are actually undefined at the two limits of omega n and omega d. Over this limit, that second term will be 0 because 1 over v phase asymptotically is flat, and so there is no derivative. So actually, I think the only difficult case you actually have to work out is probably that 0. If, however, you dived straight in and started differentiating the expression, you get some ghastly cubic, or you get a cubic divided by a quadratic or something, and you get completely lost in algebra, and you could very well spend a happy hour or two trying to sort out what was going on. The last part of the question it isn't really a waves problem at all, and I don't think I'll talk about it. Neither do I think it belongs on this paper. It's a CP3 question. So that's all I was going to say about dispersion. And I think the lesson you should take away from that is that most dispersion questions occur in section A and are relatively straightforward. They give you a dispersion relation, or they give you a sketch like that. And that's relatively easy. What this examiner chose to do was to try to invent a dispersion question to go in question B, in section B, and discovered that actually that he couldn't really do that without straying outside the syllabus. So there's probably a lesson there, although it's not completely clear what it is. So let's leave that and come on to waves. Now, what was I? That's no, I don't think there's any more on that paper. It was 2013 that I wanted, wasn't it? Where's 2013? Oh, and the other one was 2017. Right. Actually, that's another example of a slightly off-the-wall dispersion question. I don't think I'll look at that. Is this 2013? Yes, it is. 2013 question 7. 2013 question 7. Ah, okay. Right. So we have a string terminated by a wall, and so it's fixed, x equals 0, and we're putting in a triangle. They've helpfully told us it's a triangle. It's a triangle between minus 2b and minus 2b. It's then a 2b minus x. There. And then it's there. So that's the situation at t equals 0, and the wave is propagating towards. So this is a pulse that's been sent in, and it's going that way. And because we're in section A, we can probably just helpfully assume that it gets reflected negatively with a reflection coefficient of -1. So the times at which they want us to do this are at b over 2c, so it's moved a distance b over 2. So we take the same two marks, we have a peak here, and then we've got to add on to that this reflected negatively, so this is that will be a over 2, and that's a, and then this comes back down to okay, so that so what we have at that time is the sum of the input wave here, the reflected wave here, which has a kink in it here. Okay, there's a break of slope at that point there, and it steepens to go to 0. And then at 3/4, well, they are not. So that was a half b. So then they really are doing 3/4 b. So what happens then is just more of the same, actually. So that's kind of not so interesting. So here's a. So now the peak has got to here. No, I suppose it is not quite so straightforward. And the back end is there. And then that will come down and will come to here. So now what we'll have is a break of slope here. And then you observe that these two here have the same slope, so we get a flat at that point up to here, and then we get a steep slope down to there. So we get a flat portion here, and then we get this doubly steep slope at the to bring it back to the origin. And then finally they've asked where is it at B, and at B we have well, that's actually rather straightforward, isn't it, because at B we have that plus that equals that. So what's happened at time B is that this portion of the wave has vanished, and this portion of the wave has vanished, and the flat portion of the wave has arrived on the axis. And so we have precisely no displacement at all. The interesting question, of course, is where's all the energy? And the answer, of course, is it's in the kinetic energy, because this is actually moving down quite rapidly at that point. So, and that was 5 marks. Now, there was the other question I wanted to look at was a 2017 question, I think. One of the double pendulum questions I was talking about yesterday is this 2013 question here, which so what have we got here? here's 2017. And oh, the 3-mass pendulum that somebody was asking about yesterday, the 3-mass problem is 2017 question 9. But I was going to talk about this question 10. And this, I think, is a very good question, and very much it's testing. If you've got a bit of kind of physical intuition for what's going on, as opposed to just relying entirely on the mathematics to tell you, then it's quite a lot easier. And I think it's entirely fair play. So the first 5 marks, you're just deriving the wave equation, which I won't do. And then they then set up this problem, which I will try to describe. So again, we've got we have this fixed wall here, and a string, but it's not a uniform string. So this section here is lighter. So this has mass density mu, and this has mass density 2 mu. Sorry, 4 mu. We're given the speed here, so that's the mass density rho. The speed in this region is C1 is 20 meters per second. Which means that the tension, which has to be the same throughout, T is T over rho equals C squared, so T equals rho C squared, is 4 mu C1. And that's got to be the same everywhere, so it must be 4 mu C1 here. And then C is root T over rho, which is, so here it's 2 C1, which is 40 meters per second. They didn't tell you that, but we've just worked it out, and we do need to know that. So we have a boundary where the mass density changes and the speed. The mass density goes down by a factor of 4, and the speed goes up by a factor of 2. And then we're sending in a pulse with amplitude A. A for incident, and width W. So we have a little pulse, AI and width W. They're kind enough to tell you the reflection and transmission coefficients in terms of K's, which is not much use because this is not characterized by a K. So it helps to have in the back of your mind that you can also re-express that in terms of C. So if we look at the reflection coefficient that they've given us, it is K1 minus K2 over K1 plus K2. And then we remember that omega over K equals C, and so K is omega over C. And so we can rewrite that as omega over C1 minus omega over C2 over omega over C1 plus omega over C2. And if we multiply through by C1, C2 and divide by omega, we get C2 minus C1 over C2 plus C1. And that's where we're going from 1 to 2. So that's the reflection coefficient going from the string, piece of string I've labelled 1 to 2. And if you do the same for the, well, actually it's 1 going back into 1, isn't it, more to the point. So the transmission coefficient from 1 into 2 is 2, and they gave you that K1 over K1 plus K2, which turns into 2C2 over C2 plus C1. So that enables us to work out all the reflection coefficients. So the reflection coefficient from 1 to 1 is 40 minus 20 over 40 plus 20 is 20 over 60 is, sorry, I say that wrong. From 1 to 1 is 40 minus 20 is 20 over 40 plus 20 is 2/3. And the reflection coefficient from 2 to 2 is just the same thing but the other way around. It's minus 2/3. So that's for a wave going onto that interface from the other side, which we'll need in a minute. So t from 1 to 2 is 2c2, which is 80 over 60. 8/6 is 4/3. And t from 2 to 1 is twice c1, which is 40 over 8, which is 40 over 60, which is 2/3. So, they ask, let me find out what they're being asked to do, because I've gone slightly ahead of myself. All right, rewrite one in terms of speeds. We've done that. Through a series of sketches, show how the incident pulse is reflected back. So, what's going to happen? So, the first interesting time is when the pulse has completely passed the interface. So let's move over here to do that. So here's the wall, and so the reflection at this point here, there'll be a reflected wave from medium 1 back to medium 1, which is 2/3 the size. So we get a reflected wave back here, identical, so it's still got width w, but the height now is only 2a over 3. Okay? And then we get a transmitted wave with a height, interestingly, a bigger height. It's height 4/3. That's 4a over 3. One of those can't be right. Sorry? This one here. This is 1/3. Yeah, thank you. They do have to add up. That plus that has to equal that, so that can't possibly be right. Yes. Right. So that's 1/3. And now, interestingly, if we think about the situation when half the pulse has gone through, then we've got a pulse. So the maximum here is actually sitting on the boundary. What's happened to the front half? It's travelled twice as far because it's got twice the speed. So the front half is being stretched by a factor of 2. And then as it propagates in, the whole thing gets stretched by a factor of 2. So this here is wider. It's now of width 2w. So this one is going backwards, and we'll just get out of the way and won't contribute any further. This will then go up to the wall, and so at a slightly later time, we'll have this one's moved a bit downstream, and this one is coming back negative. and then it's going to hit the barrier, and so it's now got an amplitude of minus 4/3 A, and then it's going to come back into this region with a transmission coefficient of another 2/3, which will be 8/9. So then, at a slightly later stage, we will have this wave's moved a bit further over here, with an amplitude of A over 3, and then we get a negative one with an amplitude of, did I say? So it's still of width W, minus 8/9 times A. And then there'll be a reflected coefficient, a reflected pulse, which will reflect with amplitude, well, we've got minus 4/3 times minus 2/3 will give us 16 over 9. And then it'll reflect back with a negative sign with minus 16 over 9, and then another 2/3, which will give us minus 32 over 27. So the next one will come out with minus 32 over 27, and so on and so on. So we end up with a positive reflected pulse and a whole train of negative reflected pulses of diminishing, no, but not be 32 over 27. That wouldn't be a good idea at all. How did all those numbers less than 1 get to that? So, yeah, so what I didn't draw in was the reflected wave here, which was coming in with 4/3, and then, sorry, it was coming in with minus 4/3, and then reflected with 8/9. So that's double width, 2W, 8/9. And that will come back with minus 8/9, and then transmit again 16 over 27. That's where I went wrong. Okay, 16 over 27. And if you think about it, these negative pulses form, the amplitudes form a geometric progression. Because each successive pulse, so one of them goes through T1 to 2, T2 to 1, and then the next one goes T1 to 2, R2 to 2, T2 to 1. So each one is, they successively get multiplied by an extra factor of the reflection coefficient at this boundary from 2 to 2, and a minus sign from here. So each time they get smaller by 2/3. So 8/9 has become 16. Minus 8/9 A has become minus 16 over 27 A, and so there'll be a whole sequence of those, and the nth term will be minus 8/9 A times 2/3 to the n. So we get a whole sequence of pulses coming back, getting smaller and smaller and smaller. Now, somewhere much earlier in the question, we showed that the energy density in the wave is proportional to its amplitude squared. So the energy of the wave in here is obviously related to the energy of this pulse here, but because it's a different shape, it's twice the width. It's not quite so clear. But the backwards going ones, when they've reflected, they all have exactly the same functional shape, but they just get scaled. So relative to the incident wave over there of amplitude A, we have a over third minus 8 ninths minus 16a over 27 and so on. And the energies will just go as the squares of those numbers. And so what we should find is that a squared should be equal to a squared times the first reflected wave, 1/3, square it will be a ninth. The second one, 8 ninths, sigma n equals 0 to infinity. This amplitude here, which is 64 over 81, 4 ninths to the n. And that geometric progression, so 1 ought to be equal to 1/9 plus the geometric progression of whose the first term is 64 over 81, and the geometric ratio is 4 ninths, so it's 1 minus that doesn't look promising. I want 8 ninths out of this. Ooh, that's annoying because it worked out yesterday. 1 minus 4 ninths is 5 ninths is 9/5. I've got a 5 on the bottom. What can I do with a 5? So I'm going to go with 5.
1 over 3 to the n, or 1 square over 3 to the n. The reflection coefficient should also be minus 1 over 3.
Yeah, problem was certainly right. Yes, because they're the negatives of each other, aren't they? Yes, yes, you're absolutely right. Yes. So, yeah, so that wasn't 16 over 27, it was 8 over 27. And that was 1/3. Well, that's a much nicer sum. Thank you very much. We do get good undergraduates, don't we? Right, so 1 minus a ninth, and so that is a ninth plus 64 over 81 times 1 over 8 ninths, which is a ninth plus 64 over 81 times 9 over 8, which is 1/9 plus 8 ninths. Good. Right, well in that case, having arrived at the right place at the right time, I think I'll stop. So, I haven't discussed the actual derivation of these relations. And recently, I mean, after asking those for years, they seem to have got bored with that and doing other things, but you probably better know how to do it just in case. So it's just equating the displacement and the gradient of the displacement at the wall. But I thought this was a nice question because of the way it tied into the energy, and the last 7 marks were all about making the energies balance. So that was actually quite. It was, I think, a long question because it's taken us about best part of 25 minutes. With quite a lot of crossings out on the way, so I think that these questions are you need to make sure you're checking your working as you go along, and section B questions are really quite long and need time, so don't waste time in section A. So I think at that point I will stop talking about waves for this year. If anybody thinks there are things that I could do better next year, do send me an email, because. Or if you think there are errors in any of the handouts, I'm sure there are. There must be full of them, but I'd like to know where they are. All of the handouts are in their kind of current version and complete. Apart from the problem set, there's a third the third problem set never arrived this year, but will next year. So these lectures will be given next year, and if you can improve them, I'm very grateful to you. Thank you very much.